Hello everyone and welcome to another video. So today I'd like to talk a little bit about line integrals. The way I like to think about line integrals is, first off, why don't we just talk about normal integrals, right? So you'll remember from high school calculus that when we write something like this, right, integral of f of x dx from a to b, what we're really talking about doing is we have some kind of function, in this case f of x, and it's defined over some domain of x between x equals a and x equals b. So to help us visualize this, I've just got maybe a little quick paper cutout that maybe I'll try to just fit over this, and maybe I'll tape this up so we can kind of visualize, like, yeah, I don't know, you've got some kind of function. Maybe it looks like this, right? And it's got some domain of integration x. Let's say x goes from a to b. I'll color this in red, right? And all this symbol means, right, you remember back in the early days, is an integration. It's really just sort of area under the curve, right? It's one way you can think about this is you take a tiny little section of x, right? Let's call this maybe like this, right? Here's maybe, I'll call this delta x1, right? So this is this tiny little area like this, right? And all you're doing is you're looking at adding this area here, right? And we see that this area, it's this width times this height, right? So it's this little delta x times a approximate constant function value at that area, right? And then you do the same thing. You're just going to take another little chunk, maybe delta x2, right? And same thing. Go ahead and look at its area, and you add that. And you're just going to keep doing this, right? You're going to have some maybe delta xi here in the middle, right? And all you're doing with this is you're adding up these little chunks, right? All of these little areas to get the total area under this curve f of x, right? So remember, this is effectively giving you area under the curve, right? High school calculus, right? Okay, so now where this gets interesting, where a line integral comes in, is if you think about this, what we're doing is we're integrating along the x-axis, right? This dx, that's kind of what this means. Well, do we always have to be integrating along an axis, a straight axis? Well, not really. What if we want to integrate along some arbitrary curve? Let's call this curve C, and let's start easy in 2 dimensions. So let's define this curve C as all of the x and y points given some parameterization of how x and y vary with some independent variable t, right? So remember, we had a discussion on parameterizing curves earlier, so feel free to check out this other video if you need a little bit of a refresher on how to parameterize curves. But all this is, it's defining a curve in xy space, right? Another alternative formulation, or the way you could write this is, okay, we can say that there's some position vector r of t, which is just, here's how x varies in the x direction, here's how y varies in the y direction, and again, t varies between a to b. So again, these are just 2 different ways you can write arbitrary parameterization of some curve C, okay? So now, the idea with the line integral, it's actually really, really simple. It's, instead of integrating on this red line here, which is along an x-axis, I want to now have some function, which is now going to be the integrand. This function is a scalar function defined at each point along this curve C, okay? So literally what we're doing is we're taking some function, and instead of integrating and chunking it up along the x-axis, it's almost like you can say, I'm going to take this, and now this function is going to run along this curve. And again, this is going to be very hard for me to kind of manipulate. Do you kind of get the picture, right? There's some function defined over this xy space, right? And at each xy point, it defines some height, or you can think about it that way. In fact, instead of me trying to mangle this picture, maybe let me spin a diagram over here, and this movie will help you understand what we're talking about, right? So the red curve at the bottom in the xy plane, that's the curve C. And as you can see, this orange surface on top of it, that is the entire function defined over the xy plane, but we're only interested in the part of that curve which is directly above the red curve C. So in this case, I think I've drawn this in green. Let me just make sure I got the color correct. Yeah, that's the green curve you see. So you can see that's effectively what we're doing is we're taking this curve, and now what we're going to do is we are going to now, instead of integrating along an axis, we're integrating along this red domain, right? So it's a very, very similar idea. The idea being that, let me come back to this. we can do a similar operation along this red curve, right? You can go ahead and start from A to B, right? And you can now take a little section here. Maybe we'll call this delta S1. And above this, there is some function value. So this here is the base. The function value is the height. Multiplying the two together, it's going to get you one small little bit of area, right? So that's what we're writing down here. So you can have one base times one height, and then you can add up another little base and height here. So here's a delta S2, all the way up to, you have some delta Si, right? And all you need to do is we're gonna add each one of those chunks up together one at a time, right? So those terms are one of these small bits of the integral, the area under this curve, right? So adding them all up together, you can basically form an approximate Riemann sum, which is the same idea of an integral, but now it's over this curve C, right? We're just adding up all of these base times height, but it's along this interesting curve C, which is this red curve here, okay? So really what we can do, we said earlier, this is what you do when you're writing a normal integral, right? So now a line integral, we can write basically the same thing. It's basically integrate some integrand, which is that function we talked about, over a curve C, right? So these are the same ideas. Both of these are basically saying area under the curve. And what we're saying is that, okay, this integral, it's basically the limit as all of these small little Riemann sums shrink to 0. And we're just going to add them all up, right? So this is the same way we did the definition of an integral with a standard integral. This is now just along a curve C, okay? Now, where the magic happens is we should ask ourselves, what are these terms delta Si, right? Each one of those is one of these small little chunks along the curve. Now, if you remember from our other video, we had another video discussing length of a parametrized curve, how we can describe that. That's given by this expression. As long as you know the parameterization of x and y with respect to t, you can find the length of a curve between a point t equals a and t equals b using this integral. So this little L, we can basically substitute this for each one of these delta Si terms, right? Because each one of these is going to tell you how long each one of these little chunks here along the curve are. So basically, this term here, we can just plug this in for these delta Si terms, okay? So if you do that and you take the limit as it goes to 0, you end up with this expression down here. So what's great about this is, again, on the left side, this is the nice idea of what is a line integral. This is the nice conceptual, academic idea of, okay, you're just going to integrate some function along the curve C. But the right-hand side is actually the explicit formula or recipe, so to speak, of how to actually calculate that. So all you have to do is evaluate the function along the parameterization, right? And multiply it by this term, which is effectively accounting for the distance or the measure or all these delta Si terms, right? So here we are. This is the expression of how to compute a line integral if you are given the parameterization for this curve C. So again, it might be easier, again, please check out the description of this video if you want to link to some of the lecture notes and any code that we're going to show so you can follow along the discussion. What I would like to do now is, let's go over a couple examples of how to use this formula to calculate the line integral. All right, so let's look at a couple of examples. So again, I've wrote our formula for calculating the line integral up here in this box. So let's look at one example. So here, let's consider this function, 2 plus x squared y. So again, this is the surface that's lying over the xy plane, and we want to evaluate the surface along this curve C. So the curve C that I'd like to consider is the upper half of the unit circle, which I've kind of drawn here in red, right? It's just half of a unit circle on the top, okay? So I want to evaluate this function over this red curve, okay? So the first thing we got to do is we got to parameterize this curve C, and I think since this is pretty obvious, I think everyone will agree that a very convenient parameterization for x is just cosine of t, and y is just sine of t, okay? And what I'm going to do right off the bat is, remember, we're going to need to take the derivatives of those parameterizations with respect to t. So you can take the derivative of this respect to t, so you get dx dt is just negative sine. take the derivative of this with respect to t, so dy dt is just cosine, okay? And all I'm going to do is I'm going to run this parameterization from a equals 0 to b equals pi, right? That's the range of the parameterization. Quick note, maybe it's kind of interesting to think about here, but by picking this range and this parameterization, we've kind of given this curve a direction, right? Because here's where when t is equal to a, and here's where t equals b, right? If we're integrating from a to b, you can almost think of us as we're integrating in this direction, right? So this kind of has a directionality at this point now that we've picked the parameterization and the limits, okay? Okay, so that's all great. At this point, we basically have everything we need in this expression, so let's just turn the crank, okay? So the first thing we got to do is we need to plug in into this function the x and y parameterization. So everywhere you see an x, replace with cosine of t. Everywhere you see a y, replace with sine of t. So that's what I've done right here. Okay, and then we got this square root of this thing, but we already calculated the derivative. So again, plug those in right here. And I think what you'll notice is it's kind of interesting is that a few of these terms, in fact, this entire term over here, right, you can see this basically turns into sine squared plus cosine squared. So this is basically 1. Right? So this entire thing goes away. You're just ending up with this over here. And again, if you run over, if you could do this definite integral in your head, that's great. I ran a Mathematica to do this, and you come up with this answer. Great. So here is the integral. And again, the physical interpretation of this in this particular case is, if you think about this surface lying on top of it, what this number here, it's area under the curve, or you can think of it as the surface area. If you think that there's a surface lying on top of this and drops down onto the curve C, this is the area of one side of that curtain, right? It's not the total wetted area of that surface. It's on one side. Again, think about it, it's just area underneath the curve, right? That's what this is giving us, okay? Okay, let's look at another example where the physical interpretation of the line integral might be different depending on what the problem is describing. So let's consider that exact same domain right now, but what I want to think about is, what if this is the shape of like some wire that I've got? I've got a wire which is bent into a perfect semicircle like that. What makes this wire interesting though is I want to consider that the density, the linear density of the wire in terms of kilograms per meter, okay? That is dependent on how far away you are from the y-axis. So when y equals 1 up here, I want the wires are going to be infinitesimally thin. But as you get going this way, you increase density of the wire. So I guess if I'm going to sketch this, I guess I can do this in yeah, sure, let's do this in maybe in another color, green. The wire, you think about it as being really fat here, but as it goes up, it gets thinner and thinner and thinner and thinner. So geez, I'm not a great artist, but hopefully you kind of get what I'm trying to illustrate, right? You've got this wire where the thickness it's an interesting, or the density, I guess you can say, it's an interesting shape. The wire is more dense, or I guess you can think of it as thicker, down here, but as you move up towards the y equals 1 line, it gets thinner and thinner and thinner and less dense, and you know, and I'm going to describe it like this. So here's the linear density, and again, remember, this is in units of kilograms per meter, okay? That's what this function is going to return for us. So this k, it's just some constant that you can crank up or down depending on how you want to tune this or how much what the density actually is. It really doesn't matter. Let's just consider k to be just some constant, okay? So this now is measuring the linear density in terms of kilograms per meter of this wire. So one natural question might be, what's the total mass of this wire? So what I want to do is I actually want to integrate the linear density along this entire length, right? Because effectively, if I multiply the kilograms per meter times the total length and integrate along that direction, that'll give me the total kilograms or the total mass of it, right? So again, all I want to do is integrate along this curve. So again, here's the English, high level idea of what I want to do. I just want to integrate this linear density along the curve C. That'll give me the total mass in terms of kilogram of this wire. Well, it's just the exact definition of the line integral we've got over there. So just plug it in. I basically need to evaluate this density function here along my parameterization, okay? So here's our expression. right? So again, y in this case is just sine t. So sine t goes here. These terms we already know. In fact, we already did this earlier, right? Plug this in. This entire thing turns into a 1 in this particular case. So you end up with this. I can pull the k out in front of the integral. And again, you turn the crank, you're going to get this. So this is basically giving us the total mass of the wire in this case. So it's another location where now the physical interpretation of what the line integral returns to us is a little bit different in this particular case. So you can either think of it in some situations it's giving you area under the curve, but if you set it up differently, it could give you other things like total mass of a wire in this case. So I've got another small example in the notes if you want to tug on this thread a little bit more. But instead, give me a second to erase the board. Let's extend this now from a curve in just 2 dimensions to what if this curve was in 3 dimensions? Okay, so let's extend this now to 3 dimensions. So again, here's our expression for 2 dimensions. So now what we're saying is that this function f of x, y, it's now actually a function of x, y, and z. Okay, and with a little bit of thinking, and if you go back to how we derived the 2D expression, it's basically virtually the exact same thing. So I'm just going to modify this here. So now it's the function evaluated at the x, y, and z parameterization. So let me just kind of make a little bit of room. X, y, and z. Okay, then this term, you just have to tack on the plus d, plus dz of t squared. Now dt. There you go. So really it's just one, a very, very small modification to extend this to 3 dimensions, okay? And I'll leave that as an exercise to the reader to kind of verify that, yeah, this is actually the small modification you need to make, okay? So again, let's make the observation that, all right, the other way you can think about this parameterization of x, y, and z is we can talk about a position vector r, which has x, y, and z components in the I, j, k direction respectively, right? And again, we can take the derivative of this with respect to t to get r prime of t, right? The derivative of this position vector with respect to t. So you just take the derivative of each one of these terms in turn. Now what's interesting is if you look at this expression, notice that this is a vector, right? Here's the x component, y component, z component of the vector. You can get the length to take the 2 norm of this to basically compute, okay, if I want to just take the 2 norm of this, it's basically x component squared plus y component squared plus z component squared square rooted, right? That's how you do that. So you end up with this expression. If you notice, this is exactly this term here, right? So a more compact way to write this is actually what? This here is the function evaluated at this parameterization, right? So that's this part here. It's f at r of t. So this is a more convenient, more compact way to write this. And then this whole thing of this square root of all this gobbledygook, you can just write this as norm of r prime of t. That's this right here. So this is a more compact way to maybe express the line integral in 2 dimensions or 3 dimensions, right? We could have done this earlier in the 2D step, but now I think it's a good time to introduce this because I think we're pretty comfortable with it at this point. And this is the generic, compact way to represent a line integral, right? All it says is you're given some function. All you got to do is parameterize that function, evaluate the function at that parameterization, right? And then multiply it by the norm of the r prime vector, and then integrate away. That's the turn the crank method. Okay, so let's look at an example of this. So let's extend our idea. Let's say we've got some integrand here. Here's the function, okay? It's a function of x, y, and z. In this case, x doesn't show up, but that's beside the point, okay? And I want to evaluate it along some curve c where the parameterization is given by this here. So x is cosine, y is sine, z is t, and I want to run, oops, I think I forgot to write this down. I want to run all of this from t in the range of 0 to 2 pi. Okay, so if you think about this long enough, this is basically it's one turn of a circular helix which rises from the ground up. And instead of me trying to draw it on the board, I'll show you a picture of it over here so you get a rough idea of what this looks like, right? It's again, like I said, it's one complete turn of a upward moving helix. Okay, so all I want to do now is I want to evaluate this integrand over this curve C. Okay, so again, all we got to do is just turn the crank, right? We have this here in blue, so I'm just going to rewrite that right here. Okay, so I now know the limits are from 0 to 2 pi. Okay, so the first thing I'm going to do is, okay, what is the function evaluated along this parameterization? Okay, so here's the function. It's just y times sine of z, correct? Okay, and that, if I evaluate y, I know y in my parameterization case, it's sine t, and then I have sine of z. What is z in my parameterization case? It's right here. Z is just t. So we end up with just sine t times sine t, right? Okay, and then let's go ahead and grab this term, this square root stuff. Again, we can get all of these derivatives of the parameterization of x, y, and z with respect to t. I'm just going to do this right here. So take the derivative of cosine with respect to t, you get minus sine. Take the derivative of sine of t, you get cosine. Take the derivative of t with respect to t, you get a 1, right? So this whole integrand turns into this, right? Sine squared plus cosine squared plus 1, right? Which, again, we make the notice that this part right here is just 1, okay? So this whole thing boils down to this, right? And I'll let you go through, if you want to keep turning the crank here, you can apply a little trig half angle identity if you're interested in making this a little easier to do by hand, or just, again, run to a computer tool, plug this in, and you end up with some number. Square root of 2 times pi. And again, what's interesting about this is, now in this case, you can't really talk about that being the area under the curve, right? Because the curve now, the curve is in 3 dimensions, and this function f, you know, who knows what it's actually measuring? Unless this is measuring literally the distance away from the curve c, this end result is a little bit more difficult to physically interpret, right? Now, that being said, give me a second to erase the board, and let's actually talk about a case where the line integral makes a lot of good engineering physical sense of what we're evaluating when we have a curve in 3 dimensions. Okay, so now I'd like to look at performing a line integral over a vector field now. So what we mean by that is, again, let's consider that we've got some curve C here in this case, 3-dimensional XYZ space. But now what we're doing is also in this XYZ space, let's assume that there's a vector field F bar. It's drawn here in blue. I kind of arbitrarily drew this like this, right? So what we're talking about doing here now is saying, well, what if we're here on this curve, and as we move along this curve, you can pick any point along here. Like, let's say there's like a particle sitting on this curve right here, and it's moving along this curve. And as I think everyone will agree that there's some tangent vector to the curve here. Maybe let's call this t bar at some ti, right? So again, this is a tangent vector, and again, we had a discussion on tangent vectors and how to get those. Remember, we had a previous video on computing the tangent vector to a parameterized curve. So getting this tangent vector is not a problem. We have an expression for that, and we're going to look at that in a little bit. But abstractly, you can easily just think that, the particle's right here. It's going to move in the direction of this tangent vector, right? And at the same time, there is some force field vector, or some of this f bar vector, right? It's, maybe it's in some other direction at this point, right? So here's f at the point ti, okay? So as you can kind of see, there's going to be some work done by moving along this direction, which may or may not be aligned with the force vector, right? So what we could do is we can say, okay, I can look at the force at some point x, y, z, I that I'm interested in, and I can multiply the force vector, or in fact, actually take the dot product, right, of this force vector with the tangent, the unit tangent, right? So this t is, again, this unit tangent that we were talking about, right? And then we will scale it by the curvature, or the distance that it's moving at that point, right? Delta SI, right? So again, what this expression right here is you're basically dot producting force times distance, right? So this is like a little bit of infinitesimal work, right? That is done moving along this curve C some tiny distance through this force function, this vector function f, right? Okay, so that's what this looks like. It's a little bit of work. So I think everyone will agree, this is just like we did with the line integral. You can take a Riemann sum of, take a little bit of work, a little bit, and then take the limit as all of those little bits, the distances go to 0. So we can formulate that the total work that's done by moving from point t equals a here to t equals b through this curve through this vector function, it's just the force, the vector function, right, dotted with the unit tangent along the curve C, right? So, yeah, that's what this is, right? Again, you can also abbreviate this. I'm just going to write it like this. This is the force dotted with the tangent along the curve C, okay? Now, let's look at a couple of terms in this expression, right? So if C is parameterized using our standard parameterization we talked about, we're just going to denote it as some position vector r, which has an x, y, and a z component. Then, if you remember our discussion on the unit tangent vector, we had derived and showed earlier that this unit tangent vector t, it's just given by r prime over the norm of r prime, okay? So in that case, if I substitute this into this over here, right? So here's my unit tangent, just substitute this expression in, you get this, okay? And now, the other thing to remember is we had a discussion here in our other video on arc length, right? Where in equation 2.4 we showed that ds, right, this infinitesimal distance, I can represent this as r prime norm times dt. Okay, so again, substitute this in for ds, you obtain this, you see that these then cancel, right? So our overall expression for total work done now becomes this guy, right? So work is now a really handy notation that all I have to do is evaluate the vector function along the parameterization and then dot product with the derivative of the parameterization and then integrate with respect to dt, right? Oh, actually, sorry, did I miss some notation here? No, that's still probably reasonable. Yep. What I was going to say is, you know, at this point, you could make this limit, instead of just C, I could say it goes from A to B, right? Because now that is the limits of my independent parameterization variable t. Okay? So a lot of times, you might see this abbreviated like this, because really, if you stare at this long enough, it's just, again, the idea is pretty simple. It's basically force times distance. Right? So sometimes you'll see it written like this, where again, here's the force, right? Dotted with then dr, but then they'll have a bar notation to denote that the direction that you're integrating along is really a vector, right? This distance is a vector, right? I don't really like this notation as much. I feel like this is a lot more explicit. So usually I'm going to go with this for all of our examples. So again, let me just erase some of the blue. We'll get this clean. This is kind of the nice turn the crank formulation of how to get this. And again, this has a very nice physical engineering representation. When you evaluate this line integral of this vector function, right? You're taking the line integral of the vector function along this curve C. What you're physically doing is we're computing effectively the work done by, you can think about it, a work of some particle moving along that curve C through that vector field F. Right? The other way you can we can come at this from another direction if you want to see another approach is, let's go back to what we were talking about at the beginning of this lecture, right? We had the line integral of a scalar function. We were talking about, okay, one interpretation is it could be the area under the curve, or, you know, in that case of that wire, we could talk about integrating the linear density to get the total mass. Well, let's take a look. What if we considered the integrand in the line integral of a scalar function? What if we considered that quantity that we're integrating, right? Because all the line integral was doing, right, and in fact any integral, right, is you're just accumulating a little bit of stuff along the direction of integration, right? What if that little amount of stuff was a little bit amount of work that is done at each step? Just like what we were doing right here in this formulation, right? We're just accumulating little bits of work. So again, let's come back to our equation that we talked about at the beginning of the discussion. This is your normal line integral of a scalar function. So this lowercase f, it's just a scalar function. Notice there's no bar on top, right? This is the integrand here is the little bit of whatever you are accumulating, right? Well, what if we consider that little bit of stuff we're accumulating to be the work done moving along that path, right? So in other words, this integrand value, little f, it's just going to be, again, force dotted with a displacement, right? So that's what I'm going to consider as the integrand. So all I need to do then is plug this into my expression over here, right? So take this right here and plug it in for the integrand. That's the thing that we're accumulating in my line integral, right? So just plug it in here and you end up with this expression, right? So this is the integrand again. So here's the integrand. You plug this here. In fact, this is maybe the nicer version of what to plug in up there. Sorry, I probably made that a little bit more confusing. I should have waited till I simplified it down to here. Again, this is just the force dotted with the distance. Okay, but you plug this into that expression up here for the integrand, and then you end up with this, right? And you see that these cancel again, okay? And again, we end up with, if you compare what's left over, right? In fact, let me just erase the parts that cancel. And actually, I can rewrite this. Move the dt over, right? So you end up with this dt. Right? And if you compare this with this, where was it? Right here. Exact same thing. So in both cases, we're calculating work, total work done. So again, I like this because it's a nice, easy physical understanding of what's going on. So let's go ahead and look at an example of this. All right, so let's look at a quick example. So let's go ahead and just, assume we've got some vector field or some force field that looks like this, right? And what I want to do now is I want to calculate the work that this field does in moving a particle along some quarter circle defined by this. So the position vector is just cosine of t in the x and sine of t in the y. And t runs from 0 to pi over 2. So I've kind of sketched this right here. You can kind of see this is just a quarter circle. C is here in red. This F field, I've tried to draw it a little bit here in blue. In fact, this is kind of a horrible approximation of it. In fact, maybe what I should do is let me just show a screenshot of what the picture really looks like. I sketched this in Mathematica, and this is really what's going on. So you can see that we've got a particle moving along this curve C, and as it does, it goes through this, it is encountering either resistance or maybe the force field that's helping it along. I don't know. We're actually gonna have to figure that out right now. Maybe the first thing we can do is actually to make a note that by choosing these limits, so if this is A and this is B, notice here when A is 0, right, you have the point, what, this is 1, 0. So down here, this is A, right? And then B, when t is pi over 2, I think you end up here. So here's B. So again, we've chosen an orientation or a direction of this curve C. So maybe we should label this right here like this, right? So as I integrate from A to B, the particle is going in this direction. And you can kind of see right off the bat, it's actually mostly opposing the motion of this vector field, okay? So keep that in mind. We're gonna come back to that, all right? So this is the physical setup of the problem of what's going on. I just want a particle starting down here. It's gonna go through this quarter circle arc, and it's gonna move through this vector field. And I wanna know what's the work that the vector field had to do to move that particle through that, through that path, right? Okay, so here's our parameterization of this curve C. Right off the bat, we can get r prime, right? I'll just take the derivative of the x component and the y component. So here we go. Here's r prime of t, right? It's negative sine and cosine, okay? So I left our expression here for our work over here in the top corner. Let's just start plugging in terms to this, okay? So here we go. The first term that we end up with, this f of r of t, it's just the function, right? The vector function here. So everywhere you see an x squared, plug in our parameterization for x right here. So this becomes cosine squared, right? And then the y component of the vector field here is just negative xy. So that becomes negative cosine times sine, right? Here we go. So here is this first term, f of r of t, right? Then I got it dotted with r prime of t, which we already got up here. So here's r prime of t. So again, make sure we note that this is a dot product or an inner product operation, right? So it's just this times this plus this times this, right? So that's what we end up with down here. And you notice this is actually not too shabby. In fact, that's fascinating that both these terms come out the same. So I can basically combine them, pull out the negative 2 in the front. And again, now turn the crank, run over to Mathematica, go ahead and evaluate this. This is just a definite integral at this point, right? And you end up with this number. W equals negative 2/3. And again, remember we talked about how think about that. The sign, the SIGN of the result, it's a negative number, which again makes sense with our picture over here because we saw that the particle, it's mostly opposing the motion of this vector field, right? So the work should be negative, right? Because it's going in the opposite direction as the vector field, right? Okay, now, while we're staring at this actually, maybe I'll leave this as a teaser for the next video, is I'm sure you're asking yourself right now is, okay, it took negative 2/3 joules or whatever amount of energy it took to move from point A to point B. What if you had taken a different route? What if I had gone, straight to there? Would I still have that, or is this maybe a more efficient route? Or, do you take some other route like this? Right? There's many paths that you can take that go from point A to point B. The question would now be, do all those paths take the same amount of work or not? And again, we're going to take that into account and discuss that in our very next video. But okay, back to the discussion here. Let's maybe close this discussion here on line integrals. Let's talk just about a couple of general properties of line integrals. And unsurprisingly, they behave a lot like normal integrals, right? Meaning if you have some constant k here, you can actually just pull that k out of the integration and just deal with the normal integration of the line integral like we just did. Okay, that's pretty simple. Another one, what if you had two vector fields added together and then you had some path C going through the combination of these two vector fields? Well, what you can actually do is, same thing, you can do a separation and you can just integrate the path C through the first vector field and then add it when you integrate the path C through the second vector field, right? You can add them together in this kind of linear fashion. Similarly, just like how in a normal integral you can integrate, instead of going from start to finish all the way in one chunk, you can go from start to some intermediate point and then integrate from the intermediate point to the end. That's just the same way here, but the only thing to keep in mind is that when you break up this path C into maybe two of them, like a C1 and a C2, make sure you keep the orientation of C1 and C2 in the same direction as C. Just like we saw right here, if you were to break up the original path, right? So let me erase these extra paths that we drew up, right? You could go ahead and take this C and you could break it up. Maybe I'm going to do this little bit first and integrate and call this C1, right? But I got to make sure that when I do C2 here, this C2 also has to have the same orientation or the same directionality so that we don't add and subtract work inappropriately, right? Okay, so there you have it. I think with that being said, this is probably a good spot to leave it. This is our first discussion on line integrals. Like I said, the very next video, we're going to talk about extending this idea of line integrals and examining some other more interesting concepts of where we can go with this. So I hope I'll catch you at this future discussion. Remember, the new videos come out every Monday, and I hope to be able to see you there, and we'll all learn something new together. So until then, I think I'm going to sign off. Thanks. Bye.